Today we're going to go over the ideal gas law, which is PV equals nRT. That's the big one. We're also going to go over kinetic molecular theory of gases. So there are 4 assumptions, 4 to 5 assumptions, but I'm going to go over 4. Those are like the big ones that I learned. And we're also going to go over molecular speed. We're going to go over deviations from the ideal gas law. We're also going to go over effusion and also diffusion as well. All right, so gases. So for gases, they are basically 99% empty space, which means if you have like this like container of gas, right? 99% of that is empty space. So only like 1% is made up of actual like gas molecules. So the gas molecular volume is a small part of the overall volume of the gas. And the size and the shape of the container ultimately defines like the gas volume. So where does the gas volume come from? So when the gas molecules collide with the walls of the container, and that creates the volume and the pressure. So like if you didn't have a container of gas, if you have like let's say you were to analyze the gas that's in your room, right? Like the air that we breathe, then like I guess like your room would contain that gas, and that would be the volume of the gas, right? But if you were to let it out into outer space, then there is no volume, and it just becomes like a free flow of particles of like gas molecules, I guess. So like the volume is really just the container, like how big the container of the gas is. So the push on the container surfaces from the wall collisions produces the pressure of the gas. So, like, you know, when we talk about pressure, it's really about like how hard the gas molecules are pushing on the walls of the container, the surface of the container. So as you can see here, there is hold on, I'm gonna get my pointer out. There's a picture of like a gas, basically. If this was in 3D, you would see it in a box or cube. But you can see here that the gas molecules, they're bumping into the surfaces, into the surface of the container. And that bumping into the container creates the pressure and the volume. It creates the pressure. So yeah, the speed of the and also the speed of the molecules affect the pressure. So if you think of this, if you think think of if you were to hold on to a sphere of marbles, okay, and if you were to shake it, right? If you shake it gently, the marbles are just bouncing around like with like slow speed, right? But if you just shake it very violently, and if the marbles were to bounce at super high speed, it creates a lot of pressure on the container, right? So like how fast the molecules bounce, it basically defines the pressure of the gas. So yeah, in all gases, they follow the same bouncing rules. So it doesn't matter if it's a helium gas, doesn't matter if it's an oxygen gas, they all follow the same like gas rules. Okay, a much higher pressure would make the gas deviate from ideal and collide with each other. Yes, that is right. I'm gonna go over like deviations in I think a couple of slides after this, but yeah, that is very true. Yeah, so like there's a point, it's kind of like a tipping point where there's this, like once you get to the super high volume, right? Super high pressure, it becomes so pressurized that it resembles a liquid. You know, it resembles, so you know liquids, they have more pressure because like the molecules are more tight, they're more tight together, and they like, you know, they're not like free flowing like gases. So like if you like have high pressure, that means all the molecules are kind of squeezed together and it resembles a liquid. So therefore it would not be like an ideal gas. It would not behave like an ideal gas when it is more like a liquid. I hope that makes sense. But we're gonna go over that more later. Okay, so the ideal gas law is PV equals nRT. This is something that you can like just like say it to yourself over and over again, and it will get into your head pretty quickly. I know on the AP exam, this was just something that this was like the backup equation, or not the backup equation, this is like the equation that I applied to basically on any like gas question, like in the AP exam. because like it's just so universal, right? It covers so many different concepts. And sometimes when you blank out on an AP exam, you can just look back to this equation. You can think, oh, so I increased the gas, so therefore either my pressure or my volume will have to increase. Like, you know, so like you can kind of see that correlation. All right. So anyways, the P equals the volume. The P equals the pressure. The V equals the volume, and the T equals the temperature, and the N equals the number of moles. So you want to remember this is N is equal to moles, right? It's not equal to grams. Okay, so the gas constant right here is the R, and here we have 3 different values of R. They are essentially the same thing. They're just in different units. So you can see here, like, so usually if you look at a problem AP test, they might give you certain values that like fit into either 3 better. So like if they were to give you all joules and all kelvins and all moles, then you would use this this value of R. It will be the most convenient. And if they were to give you all liters, all torrs, and so on, like you would use this. So this is kind of just like whatever units they're using and whatever units will be easiest for you to use, then use that R equation, but you use the R value. But usually on the AP exam, they will use either this last one or the first one. I think I left out an ATM. I'm not sure. I believe there's an ATM right here, but this is on the AP chemistry equation sheet, which you will get in the exam. So you'll have this like value all there. So you do not have to memorize the R values. They're all on the AP equation sheet. But you do want to know where they are. It's for kg. Oh, so kg as for kilograms? Okay. I'm not really sure about that. I don't really know what 3RT over M stands for. I was just suspecting that like this first equation that I have here, 8.314, I think I'm missing a pressure value in here because I don't see a pressure. Or maybe that's a J. What, that's joules, I believe. I might be wrong. But I believe that is joules. But yeah. Okay, so anyways, these 3 are like the top, or these are the 3 R values that you're going to get on the AP exam table. So you're going to have that in the exam. So you do not have to memorize the gas constant like values. You do not have to memorize all this. You do need to memorize the ideal gas law, though. That's very, very useful. It has to be like second nature to you. All right. All right. So pressure. Yes. So pressure. We usually use the unit atomic, the ATM as the pressure unit. Sometimes we use these like torrs or Hg as well. All right. So, but like usually, so like this, these are the converges. Our teacher makes us memorize them for quizzes. Oh wow. Wait. So what does the R stands for? Like for your 3RT over M? Is it the gas constant? Oh, okay. Wait, so what does the M stand for? Is it the mass of the gas? Oh, okay. Oh, wow, but that's very good that you know like what the gas constant means. Yeah, I think I learned about that, but I kind of forgot because like it's not very, because we treat it more as a constant. It's like something that like we solve for once and then we kind of just don't use it. We don't think about like where it comes from anymore, but it's good that you know that. Yeah, so that's what the constant is, and we just use it in the ideal gas law. Okay. Yeah. All right. So for temperature, so for all gas equations, okay, when it asks for the temperature, always use kelvins. Do not use Celsius. Do not use Fahrenheit. The AP exam, they're gonna give you Celsius. A lot of times they're gonna give you Celsius. You better watch out. So always like remember to convert it back to kelvins if you ever see something like Celsius. All right, so move on. Yeah, so this will all be on the AP exam equation sheet, but do not rely on it during the exam. I think the best thing you can do is to familiarize yourself with the AP exam equation sheet, so you kind of know like where all the equations are. But that's until April. So all right, so we're going to do a little bit of ideal gas practice. So PV equals nRT. So let's calculate the pressure of 8.0 grams of oxygen gas in a 2.30 liter container at 25 Celsius. So first of all, you want to see here, okay, we see Celsius, right? We have to convert it to kelvins. So first we're going to list out the equation. So PV equals nRT. We can manipulate it so that we have P on one side of the equation and nRT over V on the other side. And then, okay, so and over here, we have 8 grams of oxygen. So we know that 1 mole of oxygen gas, which is O2, it is equal to 32 grams of oxygen, right, or O2. So therefore, we come out with 0.25 moles of oxygen gas. Are you following along with this? So yeah, we're just trying to convert it all into moles so that we see, like, so that we get the N. Got it? Okay. And then the volume, we have liters right here. And for the temperature, we have 25 Celsius. We want to convert to kelvins, and that is 298 kelvins. All right. And for R, so we're going to use the equation that has the liter unit and the ATM and the kelvins and the mole unit. Is that all making sense? So, okay, so you can see her ATM, that unit in the end transfers to the pressure unit. So we don't have like, so over here you can see we don't have like a pressure over here. That's because the gas constant, after you multiply all these in, or you divide it over V, in the end, like the ATM comes out. And the L cancels. So, so yeah, that's how the equation works. So basically you want to match up the R constant, like the one that has like the units that match up with what units you have. All right. Okay, so all right, so then after we will plug all those values in. So we have 0.25 moles, which is the amount of gas, which is equal to the N over here, the N. We're going to multiply that by the R, the gas constant. We're going to multiply that by the temperature in kelvins, remember that, and then divide that all by the volume, which is 2.3 liters, and that will come out to 2.64 ATM, or atomic pressure. Hold on, atmosphere pressure, I believe. All right, and we also have to look at our sig figs, right? We want to make sure that our sig figs are all correct. So atmospheres, yeah. I this atmosphere. Hold on a sec. Atmosphere pressure is one of the pressures. Yeah, I believe it's called atmosphere pressure. Yeah, it's called the standard atmosphere pressure. Right, I just suddenly like blanked out. I know it's like atmosphere, but like I kind of forgot like what's the full name of the pressure. All right, so yeah, so then we come out to 2.6 atmosphere pressure, and that is equal to the pressure. So there we have it. That's one kind of question you're going to see on AP exam, and yeah, and so applications when amount of gas is constant and not close to condensing. So when you talk about close to condensing, it's what you said earlier on. You talked about like when there's like high pressure, right? When there's high pressure, a gas doesn't behave very ideal anymore. It's because like the molecules are so close together that they become more like a liquid or a solid. So yeah, so these applications are when the amount of gas, so we have the same moles of gas, but like the temperature is not close to condensing or the pressure isn't close to condensing. So we have Boyle's law, which at constant temperature means that like the initial pressure times an initial volume that you have will equal to the final pressure times the final volume. So this is all when like you have the same amount of gas. So like it's not like, so if you have a leak in your gas tank, right, this will not apply because you will be losing gas molecules or you will be gaining gas molecules. Depends on what you have, what kind of container you have, and what pressure there is in the container. All right, so you can see here, this is the ideal gas law, so you want to keep that in mind. So if the amount of gas is constant, we usually can just take out the n and just kind of think of these equations as like you don't have to look at the n anymore because like the n is kept constant. So this is not provided on the equation sheet, but it's very, very useful to remember. Is P times V over T equals the final P times V over T. So if you can see here, it's derived from the ideal gas law. So we know that, so if we know that the amount of gas is constant, so the n is the same for these two, these two pressure and volume and temperature results. And we also know that the R is also the same because it's a constant, right? We're not going to have a different value of R. Then we can just basically just ignore these two, the N, R, which you can just ignore them. And we know that if we were to compare the two, or they're the same gas, but like they're at different periods of time, I guess you could say. So like if you were to like decrease a container, decrease its volume, if you were to crunch up a water bottle or something, or I guess you have to, yeah, so let's say you can decrease the volume of something without letting gas like leak or letting gas in or like puncturing the water bottle. If you can do that, like this is the equation that you can use to find out the final pressure and the final volume and the final temperature. All right, so and then there's Avogadro's law. So equal volumes of gases at the same temperature and pressure contain the same amount of molecules. So yeah, so this is something that you kind of think about over and over again, but basically, yeah, so if you look at this law, right, look at the ideal gas law, you can see that it's very easy to deduce that from this law. You can see if we have equal pressure, equal volume, and equal temperature, or same temperature, like remember the R is always constant, so it's not going to be another bigger or smaller value. So then we know that the N is the same. So like it doesn't matter what gas we have, if we have the same pressure, same volume, the same temperature, we're going to have the same moles or same number of moles of gas. I'm saying. All right, so now we're going to talk about the Kinetic Molecular Theory of Gases, the KMT. So I'm going to go over 4 big assumptions. So these are the assumptions that I believe is like the overarching ones. I looked at, so like when I learned AP chemistry, I learned just 4 assumptions. So I went online and looked up like what other people learn, you know, because some people, they say they have 5 assumptions. So I looked at those, like, I think it was on Purdue's website. And the 5 assumptions, they were basically all covered in these 4 that I'm just about to list. So, so yeah, so like some of my assumptions kind of cover 2 different ideas at the same time. All right, so the first assumption that we have is most of the volume is empty space. So when we talk about gases, when we analyze gases, we assume that the gas, like most of it is empty space, right? So like basically if a gas follows all 4 assumptions, then it's like a normal gas. It's normal, it's not abnormal, it's not like close to condensing, which is one of the deviations. So you see most of the volume is empty space because at 1 atmospheric pressure, or standard atmospheric pressure, 99.9% of gas volume is empty space, and only 0.01% is molecular volume. So only that small percent is like the actual gas, or the actual gas molecule. All right, so gas molecules do not attract or repel one another. because the volume is mostly empty space. Intermolecular attractions or repulsions do not affect the linear paths of molecules. So if you think of it as this, like you have this huge atrium, or like basketball atrium, right? And we have these like small like marbles bouncing around. They're not going to attract or repel one another because gases they bounce at very high speeds, right? So they're not going to. So have you learned about intermolecular forces yet? Or intermolecular attractions? A little, right? So like in water, right, in liquids, there are like water is basically formed from or the reason that all the water molecules they bind together to form water, to form like a puddle of water, or it's all because of intermolecular attractions. It's all because the different water molecules, they kind of attract each other. They kind of bind, but they don't chemically react together, but they group together, and they're slightly polar, so they attract each other. But for gases, they don't do that. So like let's say there are two gas molecules bouncing around, right? They're not going to attract each other, and they're not going to repulse each other. So that means that they kind of act as independent molecules. They're very independent. They're not influenced by each other very easily. So yeah, gas molecules, they do not attract or repel one another, and that's because there's so much space that there's not a lot of opportunity for attraction for those things to happen. So therefore we're going to have, so the molecules are going to bounce around in their linear paths. And when we talk about deviations, that is when they do not bounce around in linear paths. All right, so the average kinetic energy of gas molecules is proportional to the temperature of the gas, right? So Ke is the kinetic energy, which is equal to 1/2 mv squared. So when the temperature goes up, the speed goes up, and vice versa. So if you think of it as this, like you have a container of gas again, and if you were to increase the temperature, if you put a burner under it, the gas molecules are going to bounce faster and faster and faster and faster. But when you cool it down, they bounce slower, right? They start slowing down. And in theory, if you think of it as this, like if you were to cool it down so much that if you were to put that container of gas into the freezer, or I guess the freezer is not cold enough, but if you were to put it down to like 0 kelvins, or very, very, very low temperatures, then it will not be gas anymore. Like the gas molecules, they'll basically form a solid up to a certain coldness level, because like if you remember this, like the difference between solid molecules and liquid molecules and gas molecules is that the solid molecules, they don't really bounce, that they don't move like they don't move a ton anymore, right? They don't have like high speeds. They basically just like vibrate against each other, right? In liquids, they vibrate more, I guess more enthusiastically, or not enthusiastically, they vibrate more. But for gases, they're like bouncing all over the place, right? They are free, like they are moving at high speeds. And so if you think of it as this, so when you lower the temperature to so low, it's freezing, it's like literally freezing, then the speed will decrease to a point where, it's basically a solid. So I hope that makes sense. So yeah, Ke equals the average speed. All right, the fourth assumption we have is gas molecules are in constant motion, having frequent and elastic collisions with the walls and each other. So, basically your gas molecules are bouncing against the surface of the container, but they're also bouncing back. So it's not like they're glue, it's not like they're those like sticky. I don't know if you've ever played with sticky hands before. It's like this little like rubber hands. But if you slap it onto the wall, it'll stick on there, right? Like gases are not like that. They basically bounce off each other. They are very elastic. So they have very frequent elastic collisions with the walls and each other. So when they bounce against the walls and against each other, they do not lose any energy in the ideal case. So in perfectly maintained temperature, no energy is lost. So if we keep the temperature the same, if we're able to maintain it using like high-tech lab equipment or something, then when the gases bump into each other, they they will not lose any energy. So they'll keep their same speed. They'll maintain their speed. All right, so this is called a Boltzmann speed chart. So have you seen this before? Because I remember when I first saw this, it was very, very, very confusing. But I'm going to explain it only for gas speeds. Yeah, so this is, so yeah, the Boltzmann speed chart, it is for gas speeds, is to chart the gas speeds. So the temperature of the is the average of the microscopic kinetic energies. So basically, you know, wait, hold on. So each curve represents a different temperature. So like, let's take a look at just the red curve, right? So we see here that on the y-axis we have N, which is the amount of gas molecules. And here on the x-axis we have V, which is the speed of the gas molecules. So let's say at 289 or 298 kelvins, which is room temperature, the gas is like the gases, they're all going at certain speeds, right? So the speed, so not all of the molecules are going at the same speed. You know, some are going a bit faster, some are going a bit slower. So over here you can see on this curve, let's just look at the red curve. This is the number of gases. So you can see over here, if like the amount of gas that's going at 0 speed is essentially 0, or 0 meters per second. But I'm just going to call it 0V, or 0 speed. Okay. The gases that are going at about, let's say this is 100, or let's say this is 80 V. All right, 80 V. You can see that is about 500 moles of gases. They're going about 80 V, 80 meters per second. But you can see over here, this is like this peak here, that is about 2,070 or 2,750 moles of gas. That's a lot. You know, that's like the most, it's like the most popular speed, right? So this is like the most gases, and it comes down to about 300 V. So you can tell here that most gases, they bounce around at around, they bounce at around 300 V. So, hold on, I think this curve is a little bit different, because I don't know why. Oh, right, sorry. Okay, sorry. So yeah, so like what I said was just correct. I was confused by this because it looked like the red, they indicated it's negative 100. Well, that negative 100, it's in temperature, but we just did over here, which is 300 V, it's the speed. So the speed is like the most popular speed, which actually when we look at this chart, it actually translates into the average speed. So the average speed, the most popular speed, is equal to 300 meters per second. Okay. So if we look at the other curves, the green curve here, like we usually just look straight at the peak. Like, okay, where's the peak? What is the most popular? Why does the high speed go down so quickly? So the high speed goes down so quickly. So okay, so that is because the red curve represents a lower temperature. Okay, so I'm going to first go over like each of the other curves. So the other curves, you can see the average, which is the most popular speed, is like 400. The blue one, the most popular, is around 700 volumes, or not volumes, velocity, the speed. So, so when you raise the temperature of a gas, okay, there's like a bigger variety of gas speeds. So when there's like high temperature, there's a lot of different, like the gas molecules, they'll all be bouncing around at a lot of different speeds. So over here you can see this is the red is the lowest temperature over here. The red curve represents the lowest temperature. So it's negative 100 kelvins, I believe. Or never mind, it's not kelvins. Not negative 100 kelvins. I believe this might be Fahrenheit. Yeah, so negative 100 temperature. there's less variety of speeds, right? So over here, you can see like when you come to around 1000 speed, there's like barely any, right? I mean, there's essentially zero. So you can see like it goes down so quickly because the lower temperature you have, like basically more gases, like more gases will move slower. But you can see here, this is the highest temperature, 600, all right? The blue one equals like 600 temperature. So that means that like there's like a wider distribution of gas molecular speeds. You can see there's more that like goes super, super fast. And you can see as the temperature goes up, like their peaks also go down, right? Their peaks also go down. So like, and they also spread a bit wider. So you can see here the blue one, its range is way bigger, and that kind of evens it out. If you think of it as this, like the average, when you spread this curve further, more wide, the average, it kind of moves with the curve, right? So if you were to spread more to the left, or sorry, more to the right, as you know, as we see the temperatures increase, they're spreading more to the right. Then the average will also move a bit more to the right, right? So if we were to take this red line and we were to drag it over here, right, then this peak will also go down, right? It will probably be somewhere around here. And that means that its average temperature will match up to like average speed will match up to 600, which means that its temperature will also go up. So a higher temperature and velocity would peak at lower number of molecules. Yes, when you look at it at like with a comparison chart like this, but if you see a chart like this, but you only see one curve, so you only see the blue curve, right? If the red and the green didn't exist, if all you see was the blue curve, then you know, I don't know what kind of question they'll ask. They might ask you, what is the average speed, or what is the what is the average speed of the gas? Then you will of the gas molecules. Then you'll have to find the average speed. So yeah. So if they were to compare these, then yeah, usually the peak is lower. But you also want to make sure that you can see here that this side of the curve is like reaching into the super high speeds, right? So if you're comparing like three curves that have the same length as this red curve, so they all reach zero at like 800. Okay, if we have three curves, but like they all have different heights and peaks, then that doesn't mean that they're at different temperatures. I hope that makes sense. Am I making sense? I think I can draw this. Yeah, so if we have three identical red curves, that's exactly like this. They have the same range, okay, or have the same domain. They all stop somewhere around here. And if there was like one that's ended up somewhere around here, but the peak ended up somewhere around here, another one has this peak around here and leveled up like this, then we know that the smaller curve basically means that there's less numbers of moles inside, or that is represented. I hope that makes sense. So in this case, we're comparing like the same gas, and we're just comparing them. Like the only variable that we're changing is the temperature. So it's like the same gas at different temperatures. All right. So yeah, the peak, they mark the average speed, which is the Ke, the kinetic energy of the molecules on the x-axis. Yeah, so the more bright the peak is, the faster the average molecules move. And therefore, the higher the Ke and temperature are. So remember, the Ke is the average, like the average speed. So we find the average speed by looking at where the peak is, and we kind of look, then we trace it down to where the V is, where the V value is. All right, so now we're going to talk about molecular speed. So we talked about how when you heat up a container of gas, the hotter it is, the faster the speed is going to be. And also, the heavier molecules, so the molecules that have greater molar mass, they're going to move at slower speed. So let's say that we have a container of gas full of hydrogen and full of oxygen gas molecules, right? They're all bouncing around. They're not reacting. They're all bouncing around. Let's say they're all at constant speed. Constant temperature. They're in the same container at the same temperature. The hydrogen molecules, they're going to bounce faster because they're lighter. They have less mass, so they're going to bounce around quicker. And the oxygen molecules, they're going to bounce a bit slower because they have more mass. And if you've ever seen the periodic table, like have you seen like the spheres where like the oxygen or the hydrogen sphere, like the illustration of the atom, it's like the smallest circle or smallest sphere, and as you go down the periodic table, it becomes bigger and bigger. The size becomes bigger and bigger, and also becomes more heavy. So, all right, so we're gonna move on. All right, so now we're going to talk about deviations from ideal behavior, and you already talked about this, so we're going to go over this. So when the gas does not follow the KMT assumptions, that is when we have deviations from ideal behavior. So let's say, this is one assumption from the KMT. The molecular volume is negligible for gases, which means that molecular volume is only it's only 0.01% of the overall volume, right? However, at high temperatures, there's a lot of molecules packed in a small space, right? That's how I like to think of high temperatures, high pressures, because there is so much less empty space to bounce around in. The pressure can become higher than predicted. So that is sometimes because the gas, they start clumping together, or they start actually not reacting, they have intermolecular forces, and that interferes with their paths. So as you decrease the empty space, there's more room for not reactions, but attractions and repulsions to happen. All right, so at molecular volume is not negligible for high pressures and concentrations. So basically, when we have high pressures, which means everything's very crunched together, the molecular volume, it's not a very, very small amount of the overall volume. It makes up more, so might make up 20% of the overall volume. So does that make sense? If you have any questions, feel free to ask. Okay, another assumption that we have for ideal behavior is gas molecules do not attract or repel each other, right? So this is when everything's going well, or going as predicted. However, at low temperatures, so when temperature's really low, the molecules, they slow down, and intermolecular attractions become strong, right? So rather than collide elastically, gas molecules may stick together and cause condensation. So they will start to form. So water molecules, right? They will, in steam, right? They're kind of in a gas state. But when you start to lower the temperature, then they start condensing. They start to form droplets. They start to form liquid water again. And this lessens the straight line motion and decreases the number of collisions with the walls of the container, which produces lower pressures than predicted. So you can see here, the gas molecules, they usually travel in linear paths. They just bounce. They're high speed, right? They don't do curves. They go linear paths. So at low temperatures, because there's intermolecular attractions, they're interfering with the paths. So so in the end, so like imagine there's like a lot of marbles they're bouncing around, but then as the temperatures get lower, they start slowing down and they start like attracting each other and they start clumping together. And then what happens at the end is they start, when they start clumping together, there's like less collisions with the surfaces of the container, right? Because imagine there's like clumps in the middle, right? There's going to be less gases that actually like bounce on the surface. So there's going to be less collisions with the surface of the container, with the walls of the container. And because there's less collisions with the walls of the container, there will be lower pressures because the pressure is made up of the collisions that the gas molecules have with the wall. So yeah, so you think of this as the wall, right? Like the more the gas molecules punch the wall, the more they collide with the wall, the greater the pressure is. But once they start colliding with it less frequently, it will lower the pressure. All right, so now we're going to talk about effusion. This is about gases leaking from an area of high pressure to an area of lower pressure through a pinhole. So over here, you can see there's like a wall. This is a vacuum, which means it's low pressure. So gas, there's like a lot of pressure over here, and there's a pinhole here, and the gas is like leaking out. So as the temperature increases in this what we call it, this cube of space, as the temperature increases, the rate of effusion increases as well. So, and that is because, when temperature increases, the speeds of the molecules, they increase as well. Okay, another rule here is bigger molecules, they effuse slower than smaller molecules. So think of this as an escape hole, right? So the bigger molecules, they're gonna go through the hole a bit slower because maybe less of them can fit through at the same time. However, smaller molecules, so like hydrogen, which is very small, is the smallest gas molecule there is. Hydrogen will be able to fit in they probably can, like 5 moles of hydrogen gas can fit in at the same time, so they will like effuse much faster. So yeah, so the bigger molecules, they have more molecular mass, which means they're heavier and they're also bigger, and they also would move slower than the smaller ones. Yeah, so the smaller ones, they have less molecular mass, so they would effuse through that pinhole much faster. All right, and now we're going to talk about diffusion. So this is about gases intermingling. So the rules are very similar to effusion. As the temperature increases, the rate of diffusion increases because, speeds, they go up. And the bigger molecule, the ones that have greater molecular mass, they move slower. So let's say gas 1 is bigger than gas 2, then which I think it is over here. So gas 1, it will move slower than gas 2. As you can see here, gas 2 already has a bunch of these small molecules over, and gas 1 has just a few, even though like the gates were open at the same time. All right, okay, so this is Graham's law of diffusion. This is not something that I actually learned in AP chemistry. And I'm not really sure if this is in the curriculum for this year. I don't think it is, because it's not like effusion, diffusion. They're not tested like extensively on the AP exam. The teacher taught us this. Okay, well, that's a very good teacher. But like this is not an equation that you have to like memorize for the AP exam. I think it's very good to know. Because I know all the diffusion laws and the effusion laws in my head conceptually, but I didn't memorize the mathematical equation. Your teacher is very he gives you guys a lot of equations to memorize, which is good, to see how they relate to each other and how these concepts can actually be translated into math, right? I think it's pretty cool to see that. So yeah, so the rate of effusion for gas 1 over rate of gas 2 is equal to the molar mass of gas 2 over the molar mass of gas 1. The square root of that. Forgot to mention that. All right, so now we're going to talk about the ideal gas. So So here's a question. Under what conditions are gases most like ideal gases? This is something that you really need to know for the AP exam because they're going to quiz you on this. So if you don't know the answer, that's fine too. Under what conditions are gases most like ideal gases? 22.4 liters. So at room temperature, I believe 1 mole or 1 mole of gas will equal to, wait, no, I believe it's atmospheric temperature. Yeah, 273 kelvins. Yes, I believe, yes, standard atmospheric temperature. Right. So yeah, under what conditions are gases most like ideal gases? But over here, we're not really talking about like what temperature is ideal. We're kind of talking about like the vague idea of like when do they behave most like ideal gases? So you could say, oh, when the temperature is higher, the gases, they're more like the best gases. You know, they behave like the best gases. Or when the pressure is, I'm giving the answer here, but it's actually high temperature and low pressure. So that means that the higher the temperature is, the more gassy it is, right? So the more the gas molecules behave more ideally. Could also lead to weak force and small size. So do you mean like the gas is becoming smaller, like the molecules shrinking? Because I don't think they can shrink. I think hydrogen is the smallest gas molecule, but I don't think you can shrink it. And I think for oxygen molecules, I don't think you can shrink it to like hydrogen size either. Not shrink it like smaller mass. Smaller mass equals more ideal. Yeah, that's right. Especially, that's right, because like I think for smaller masses, it's when you raise the temperature like just a little bit, you know, the molecules are going to move faster because they're already faster than the bigger masses. So yeah, you could say that like the mass also contributes, but like if we were to have a container of oxygen gas, we can't just, you know, trade that. We can't just pretend or wish that it is hydrogen molecules. So to get this container of hydrogen gas to behave the most ideal, then, you know, what can we do? The best thing that we can do is put the temperature very low and put the pressure low and set the temperature high. So yeah, basically push down on the, not push down, like heat up the container of gas and put the temperature low. So let the gas have a lot of space to bounce around in. Don't confine it to a very small space when you have a lot of molecules. All right, so that's the way that you can get any gas to behave the most ideally. Yeah, so high temperature and low pressure make the best of ideal gas behavior. And high temperature, because the resultant high speed will keep the molecules busy. So it means like they'll be busy bouncing around. So that way the gas isn't tempted to condense because of its intermolecular forces. Because most gases, they all have intermolecular forces. Or actually, you know what? Have you learned about London dispersion forces yet? London dispersion forces. I believe it's called LDF. Yeah, London. So the thing about like intermolecular forces is that everything has intermolecular forces. Some of them are stronger, some of them are weaker. The weakest one is called the London dispersion force. And I believe under certain circumstances, the London dispersion force is actually greater than the other types of intermolecular forces. But for most cases, the London force is like the smallest one that you can have. So like for everything, like even if it's a perfect linear molecule, even if it's like perfectly nonpolar, there's still that small bit of like London dispersion force, because like as you can remember, like the electrons are spinning around, right? They're not everywhere at the same time. They're spinning, so there's still like they can be tempted to become a bit more polar. So yeah, so high temperature will keep the molecules busy so that they're not tempted to condense because of their intermolecular forces. Gases that aren't ideal, gases are not ideal if they change into liquids or solids, right? So when we talk about ideal gases, to keep the when we want to keep a gas, when we want to keep a gas at its most ideal state, we do not want it to become a liquid or a solid, right? We want to keep it the most like a gas. So therefore, we want to not tempt it to become to condense or become liquids or solids. All right, about low temperatures, low pressure. Sorry, I'm reading everything wrong right now. Forgive me for that. So low pressure allows gas molecules to bounce around freely, and gases are best when they have room to bounce, right? So when they have more room, they have more freedom to bounce around, and they will not have too much attractions going on. All right, and that is the end of my slides.